So what we have here is my GC. So we have our injection port right here, along with our gas coming in to help push our analyte through the into the column. So if we look here, we have our oven, and then if we look at a 2D model of our oven here, we have our injection port in red, and then the gas coming into our injection. And so what we used here is a splitless injection port, and we use this because we're looking at trace amounts and high volumes, and it works very well because about 80% of the analyte actually makes it to our blue column here. And it's also very useful because it uses solvent trapping, which allows us to maintain the boiling point in our injection point just below the boiling point of our analytes, and this minimizes the head start effect. Moving forward, looking at our column, we're using a polar column, and that's because we're trying to separate out polar compounds. The temperature inside of our oven here will be hot to maintain as much of the gas phase as possible when we're looking at our analytes so they don't come out into the liquid phase while they're on the column. And we'll be using temperature programming, and that helps to separate the elements based on their boiling point. And so we'll start at a lower temperature, and over time we'll raise that temperature to help other analytes reach their gas phase and travel from the stationary phase into the mobile phase through our column. Moving on to look at our detector, we leave the column and we move into this other part here, our detector. In the red here, we have a flame ionization detector. So this will burn our compound when it comes out of our column, and it will produce ions that will hit a detector plate, this part right here. And when it hits the detector plate, it will send a signal through to our computer over here, and that signal records a certain intensity and area based on how many ions hit the detector plate. Flame ionization is very useful when working with organic molecules, and it has an increased sensitivity and dynamic range, so it's especially good for sensitivity when you're using those trace amounts with the splitless injection. The one issue is that you need to constantly maintain enough gas and air for our flame to run properly and not just die out in the middle of the experiment, so you need an instrument that supplies multiple gases at once. And then finally, just to talk about why we're using the flame ionization in a polar column, we're trying to elute methanol, ethanol, and butanol, so they're all polar, so you want to use a polar column. And since they're organic molecules, we want to use this this flame ionization, which works well with the organic molecules. And so in terms of how these will come off the column, since they're all polar, we will see them come off the column based on their boiling point. So methanol, which has the lowest boiling point of 149 degrees Celsius, will come off first. Then ethanol with 173 degrees Celsius, and then finally butanol with 244 degrees Celsius. And this happens because as we slowly raise the temperature, some of our analytes will be able to go into their gas phase while others will still be stuck in their liquid phase. And so as we raise the temperature, other ones will actually be able to go into the mobile phase of the column. And so that's why they will elute in that order.